calculate the appropriate subpanel and conductor size for powering 6 electric pallet jack chargers, we need to follow a few key steps. Firstly, calculate the total load. The provided information indicates that each electric pallet jack charger draws 12 amps. With 6 pallet jacks, the total load is calculated by multiplying the individual load by the number of units. Therefore, 6 jacks multiplied by 12 amps per jack equals 72 amps. Secondly, determine the circuit voltage. In this scenario, the connection is made to 120/208 volt 3-phase panel. This voltage is essential for selecting the correct conductor size and overcurrent protection. Thirdly, select the appropriate conductor size. Based on a 72 amp load operating on a 120/208 volt circuit, consulting electrical codes and tables is necessary to determine the correct American wire gauge, or conductor size. In this case, number 4 AWG conductors are suitable for carrying 72 amps. It is crucial to reference the National Electrical Code, or NEC, Table 310.15. B16, or other relevant tables to confirm the ampacity of the conductors based on the installation method and temperature rating. Now let's consider some additional important factors for a safe and compliant installation. 1. Conduit. It is imperative to install the conductors within a conduit to provide physical protection against damage. The type of conduit, such as electrical metallic tubing, or IM, rigid metal conduit, or RMC, or other approved types, should be selected based on the specific environmental conditions and local electrical codes. 2. Overcurrent protection. Install a 100 amp circuit breaker or fuse at the subpanel to protect the circuit from overloads and short circuits. The overcurrent protection device should be sized appropriately for the conductor ampacity and the connected load. 3. Grounding. Ensure the subpanel is properly grounded to provide a safe path for fault current and minimize the risk of electrical shock. The grounding system should comply with NEC Article 250 and should include a grounding electrode conductor connected to a suitable grounding electrode, such as a ground rod or water pipe. 4. Length of run. The length of the wire run from the main panel to the subpanel, in this case 50 feet, needs to be considered for voltage drop. However, for a relatively short distance like 50 feet and a moderate load of 72 amps, the voltage drop is unlikely to be significant when using number 4 AWG conductors. If the distance was substantially longer, a voltage drop calculation would be necessary to ensure that the voltage at the subpanel remains within acceptable limits, typically within 3% of the source voltage. 5. Summary of materials. To summarize, the required materials for this installation include number 4 AWG conductors, a 100 amp circuit breaker or fuse, appropriate conduit for physical protection, and grounding materials. Remember to always consult with a qualified electrician and adhere to all applicable electrical codes and regulations when performing electrical work. This information is for educational purposes only and should not be considered a substitute for professional electrical advice. Always prioritize safety and ensure that all electrical work is performed by qualified individuals. The ampacity of a conductor refers to the maximum amount of electrical current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. This rating is crucial for ensuring the safe and reliable operation of electrical systems. Exceeding the ampacity of a conductor can lead to overheating, insulation damage, and potentially electrical fires. The NEC provides detailed tables and guidelines for determining the appropriate ampacity of conductors based on factors such as the conductor material, size, insulation type, and installation conditions. These tables take into account the ambient temperature and the number of current-carrying conductors in a raceway or cable, as these factors can affect the heat dissipation of the conductors. When selecting conductors for a specific application, it is essential to consider not only the ampacity but also the voltage drop, which is the reduction in voltage that occurs along the length of the conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors or conductors with lower resistance can be used. Additionally, the installation method and environmental conditions can affect the ampacity of conductors. For example, conductors installed in conduit or cable trays may have a lower ampacity than conductors installed in free air due to the reduced heat dissipation. Similarly, conductors installed in high-temperature environments may require dirting to prevent overheating. Therefore, it is crucial to carefully consider all relevant factors and consult the NEC when selecting conductors for any electrical installation. The NEC provides comprehensive guidance on conductor ampacity, voltage drop, and other important considerations to ensure the safety and reliability of electrical systems. Ignoring these guidelines can lead to hazardous conditions and equipment damage. A circuit breaker is an electrical safety device designed to protect an electrical circuit from damage caused by overcurrent or short circuit. Its basic function is to interrupt current flow after a fault is detected. Unlike a fuse, which operates once and then must be replaced, a circuit breaker can be reset, either manually or automatically, to resume normal operation. Circuit breakers are made in varying sizes, from small devices that protect individual household appliances up to large switchgear designed to protect high-voltage circuits feeding an entire city. They are an essential component of modern electrical systems, providing protection against overloads and short circuits. There are several types of circuit breakers, each designed for specific applications and voltage levels. Miniature circuit breakers, or MCBs, are commonly used in residential and commercial buildings to protect branch circuits. They are typically rated for currents up to 100 amps and voltages up to 480 volts. Molded case circuit breakers, or MCCBs, are used for higher current and voltage applications such as in industrial and commercial power distribution systems. They are typically rated for currents up to 2500 amps and voltages up to 600 volts. Air circuit breakers, or ACBs, are used for even higher current and voltage applications, such as in power plants and substations. They are typically rated for currents up to 6,300 amps and voltages up to 1,000 volts. The operating principle of a circuit breaker involves detecting an overcurrent condition and then interrupting the current flow. This is typically accomplished using a thermal or magnetic sensing element. A thermal circuit breaker uses a bimetallic strip that bends when heated by an overcurrent. When the strip bends sufficiently, it triggers a mechanism that trips the breaker and interrupts the current flow. A magnetic circuit breaker uses an electromagnet that is energized by the current flowing through the circuit. When the current exceeds a certain level, the electromagnet becomes strong enough to trip the breaker. Circuit breakers are designed to trip quickly in response to an overcurrent condition. The tripping time depends on the magnitude of the overcurrent. Small overcurrents may take several seconds or minutes to trip the breaker, while large overcurrents, such as those caused by a short circuit, will trip the breaker almost instantaneously. When selecting a circuit breaker for a specific application, it is important to consider the voltage, current, and interrupting rating of the breaker. The voltage rating must be equal to or greater than the voltage of the circuit being protected. The current rating must be equal to or greater than the maximum current that the circuit is expected to carry. The interrupting rating must be equal to or greater than the maximum fault current that the circuit could experience. Additionally, it is important to select a circuit breaker that is appropriate for the type of load being protected. For example, circuits that supply inductive loads, such as motors, may require circuit breakers with a higher interrupting rating to handle the inrush current that occurs when the motor starts. Circuit breakers are an essential component of modern electrical systems, providing protection against overloads and short circuits. They are made in varying sizes and types to accommodate a wide range of applications. When selecting a circuit breaker, it is important to consider the voltage, current, and interrupting rating of the breaker, as well as the type of load being protected. Conduit, in electrical systems, refers to a tube or channel designed to protect and route electrical wiring. It provides a safe and organized pathway for conductors, shielding them from physical damage, moisture, and chemical corrosion. Conduit is typically made of metal, plastic, or fiberglass, and comes in various sizes and types to accommodate different wiring needs and environmental conditions. The primary purpose of conduit is to protect electrical wiring from external factors that could compromise its integrity and safety. By encasing the conductors within a rigid or flexible tube, conduit prevents them from being exposed to physical damage such as impacts, abrasions, and crushing forces. This is particularly important in industrial and commercial environments where wiring is subject to heavy use and potential hazards. Conduit also protects wiring from moisture, which can cause corrosion and electrical shorts. By providing a sealed or watertight enclosure, conduit prevents water from coming into contact with the conductors, ensuring their long-term reliability. This is especially important in outdoor and underground installations where wiring is exposed to rain, snow, and groundwater. In addition to physical and moisture protection, conduit also helps to prevent electrical fires. By containing any sparks or flames that may occur due to a short circuit or other electrical fault, conduit minimizes the risk of igniting surrounding materials. This is particularly important in buildings with combustible materials such as wood or paper. There are several types of conduit available, each designed for specific applications and environmental conditions. Rigid metal conduit, or RMC, is a heavy-duty steel conduit that provides excellent protection against physical damage and corrosion. It is typically used in outdoor and underground installations where wiring is subject to harsh conditions. Intermediate metal conduit, or INC, is a lighter-weight steel conduit that offers similar protection to RMC but is easier to bend and install. It is commonly used in commercial and industrial buildings. Electrical metallic tubing, or INT, is a thin-walled steel conduit that is lightweight and easy to cut and bend. It is typically used in indoor installations where wiring is not subject to severe physical damage. Flexible metal conduit, or FMC, is a flexible steel conduit that allows for easy bending and routing of wiring in tight spaces. It is commonly used to connect equipment to electrical boxes or to run wiring around obstacles. Liquid-tight flexible metal conduit, or LFMC, is a flexible metal conduit that is covered with a waterproof plastic coating. It is used in wet or damp locations where wiring needs to be protected from moisture. When selecting conduit for a specific application, it is important to consider the following factors: the type of wiring being used, the environmental conditions, the physical stresses the conduit will be subjected to, and the applicable electrical codes and standards. Conduit should be installed in accordance with the NEC and other relevant regulations. Proper installation includes securely fastening the conduit to walls, ceilings, or other structures, using appropriate fittings and connectors, and ensuring that the conduit is properly grounded. Grounding is an essential safety measure in electrical systems, designed to protect people and equipment from electrical shock and damage. It provides a low-resistance path for fault current to flow back to the source, causing the overcurrent protection device, such as a circuit breaker or fuse, to trip and de-energize the circuit. Grounding is typically achieved by connecting the metal parts of electrical equipment, such as enclosures, conduit, and grounding conductors, to a grounding electrode, such as a ground rod or water pipe. The grounding electrode is then connected to the earth, providing a direct path for fault current to dissipate. There are two main types of grounding: equipment grounding and system grounding. Equipment grounding is the connection of the metal parts of electrical equipment to a grounding electrode. This provides a low-resistance path for fault current to flow back to the source, preventing the metal parts from becoming energized and posing a shock hazard. System grounding is the connection of the neutral conductor of an electrical system to a grounding electrode. This helps to stabilize the voltage of the system and provides a path for fault current to flow back to the source in the event of a ground fault. The NEC provides detailed requirements for grounding electrical systems. These requirements vary depending on the type of system, the voltage, and the application. It is important to follow these requirements carefully to ensure the safety of people and equipment. Some common grounding practices include using grounding conductors of the appropriate size and material, bonding all metal parts of electrical equipment together, connecting grounding electrodes to the earth, and testing the grounding system to ensure that it is functioning properly. Grounding is an essential safety measure that should not be overlooked. Proper grounding can prevent electrical shock, reduce the risk of fire, and protect electrical equipment from damage. It is important to consult with a qualified electrician to ensure that the grounding system is properly designed and installed. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. It is an important consideration in electrical system design, as excessive voltage drop can cause equipment to malfunction or operate inefficiently. Voltage drop is directly proportional to the current flowing through the conductor and the resistance of the conductor. The longer the conductor and the higher the current, the greater the voltage drop. The resistance of the conductor depends on its material, size, and temperature. Copper has a lower resistance than aluminum, so copper conductors will have less voltage drop than aluminum conductors of the same size. Larger conductors have lower resistance than smaller conductors, so larger conductors will have less voltage drop. The resistance of a conductor increases with temperature, so voltage drop will be greater at higher temperatures. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Branch circuits are the circuits that supply power to individual loads, such as lighting fixtures and receptacles. Feeders are the circuits that supply power to branch circuits from the service entrance. To calculate voltage drop, you can use the following formula: voltage drop equals current in amps multiplied by the length of the conductor in feet multiplied by the resistance of the conductor per foot. The resistance of the conductor per foot can be obtained from the NEC or from conductor manufacturers. To reduce voltage drop, you can use larger conductors, use conductors with lower resistance, shorten the length of the conductors, or reduce the current flowing through the conductors. Using larger conductors will reduce the resistance of the conductors, which will reduce voltage drop. Using conductors with lower resistance, such as copper instead of aluminum, will also reduce voltage drop. Shortening the length of the conductors will reduce the overall resistance of the conductors, which will reduce voltage drop. Reducing the current flowing through the conductors can be achieved by using more efficient equipment or by distributing the load over multiple circuits. Voltage drop is an important consideration in electrical system design. By limiting voltage drop to acceptable levels, you can ensure that equipment operates properly and efficiently.